Swayam Prabha. Digital India. Educated India.
Welcome to lecture 2. Today we will be giving you some more definition that we will require. So, for example, we will discuss, last time we have seen the definition of ring and examples. Today we will talk about some properties of rings, and then we will define what is a subring, and then we will define what are the units and zero divisors in a ring. So, let us start. So, last time I have defined what is a ring, and before giving you the formal definition of ring, I have given you several examples. So, let us just recall the definition of ring that I have given last time quickly. So, if you remember, we have seen that a ring was nothing but a binary set with two binary operations which satisfies these four properties. Now, in some of the books, this existence of multiplicative identity is not considered as a property which needs to be satisfied in the definition of ring. Some books omit this condition. So, those rings are called rings without identity, but throughout this course we will assume condition 3 has to be satisfied because we are considering rings with identity only. So, just for your clarification, I will try to make a remark here that there are rings without identity as well. So, the remark, so sometimes this condition 3 in the definition of ring is not considered. So, we can define the ring without this existence of multiplicative identity. Condition 3 was existence of multiplicative identity. So, for example, if I consider say the set of all even integers 2z, okay. So, then we can see that it has, if we take two even integers and do the addition, then we will get again an even integer, and multiplication of two even integers is again even integer. So, it is not difficult to check that this is an abelian group with additive identity 0, and this is closed under multiplication, is closed under multiplication, and this multiplication is associative, it satisfies the distributive property and so on. So, all the properties are satisfied except one, that is the multiplicative identity does not exist. There does not exist any even integer, so that if we multiply it with any other elements from 2z, then we will get back that element. So, there does not exist any multiplicative identity in 2z. So, this is a ring without multiplicative identity. So, we can say that 2z is a ring without multiplicative identity. But let me put it as a remark here that in this course we consider rings with identity. So, whenever I will say ring, it is always true that multiplicative identity is there. So, for us in the definition of ring, condition 3 is already satisfied. We do not consider rings without identity. This is true for throughout this course. Okay. So, now all these properties, these 4 properties that I have said for in the definition of ring, I can talk about something more, some extra property. So, let me tell about that, and if that property is satisfied, then we call that ring to be a commutative ring. So, if the multiplication is commutative, so definition we say that if in addition of the above 4 conditions given in the definition of ring, one more property, that is A dot B is same as B dot A is satisfied, then it is called a commutative ring. And this needs to be satisfied for all A B in R. This needs to be satisfied for all A B in R. Then we call that ring to be a commutative ring. So, now you can see the examples that we have already seen in the previous lecture. Among those examples, the ring of integers, the rationals, real numbers, complex numbers, all these are commutative ring. So, let me just point it out. That Z, R, Q, C are all commutative rings. Whereas, if I would like to give you some example of non-commutative ring, then I have to go into the matrices, because matrix multiplication is not commutative. A dot B of is not same as B dot A. So, here I can say that the set of all matrices, this is not a commutative ring, as multiplication of 2 matrices is not equal always. So, this is not true for all A B in for all A B in the set of n cross n matrices. So, we have seen examples of commutative ring and non-commutative ring. Now, let me give you some properties of ring. Okay, so, properties of rings. So, what are the properties? So, let me first state those, then I will give you a proof. So, let R be a ring, let R be a ring. So, ring means with multiplicative identity. Then the first property says that A dot 0 is same as 0 dot A, which is in fact equal to 0, where this 0 is the denotes the additive identity. The second property says that minus A dot B. So, this minus A denotes the additive inverse of A. This is same as A dot minus B, which is equal to minus of A dot B for all A B in R. So, this is nothing but the additive inverse of the element A dot B. And the third property says that minus A dot minus B is same as A dot B, and the fourth property is minus A is nothing but minus 1 dot A. So, what is minus 1? Minus 1 is nothing but the additive inverse of 1, which is nothing but the additive inverse of the multiplicative identity 1. So, let me give you the sum of the proof among all these 4, and we will basically see that distributive property is helpful in proving this statement. So, I will give you the proof of the first 2 and the rest 2 you can try by yourself. So, you know that A dot 0 plus 0 is nothing but A dot 0, because 0 plus 0 is 0, which is saying same thing as, now if I apply the distributive law here, then it says A dot 0 plus A dot 0 is equal to A dot 0. Now, if I cancel out from A dot 0 on both sides, or in other words if I add the additive inverse of A dot 0 in both sides, then what I will get is that A dot 0 is equal to 0. Therefore, the first property is proved. Similarly, I can give you a proof of the second one again using the distributive law. So, you know that A dot B plus A dot minus B, this I can write it as A dot B minus B. This is by using the distributive law I can write. So, if you want I can write it in just for little bit more clarity, B plus minus B. So, this is by using the distributive law I have written, but B plus minus B is nothing but the additive identity 0. So, this is A dot 0, and by previous one we have seen that A dot 0 is nothing but 0. So, I have proved that this A dot B is nothing but the additive inverse of A dot minus B. So, from here I can say that A dot minus B is same as minus of A dot B. So, this proves the second part, and for the 3 and 4 you can try in the same way, similar way. Now, I will define what is the 0 ring. So, what is the 0 ring? So, if in a ring you have only one element, that is a 0 element, then it is called the 0 ring. So, a ring which consists of the single element zero is called the 0 ring. That means, it has only the element 0, then it is called the 0 ring. So, basically in the 0 ring your multiplicative identity, all the elements are 0, that means your additive identity is same as the multiplicative identity. And we will see now that if in a ring your multiplicative identity is same as the additive identity, then that ring is in fact the 0 ring. So, I will prove next the following, that let R be a ring, let R be a ring in which the multiplicative identity is same as the additive identity, then R is the 0 ring. How to prove it? So, 0 ring means I have to show if I take any element from this ring, then it has to be the 0 element. So, let us start with any element. So, let A be in R be any element of the ring R, then I can see that A I can write it as A dot 1, but 1 is equal to 0. So, I can put A dot 0, but A dot 0 is equal to 0. So, it says that that element has to be equal to the 0 element. That means, every element is 0 element, therefore, it is the 0 ring. So, therefore, every element of R is 0, which implies that R is the 0 ring. So, we have seen that if you have a ring where multiplicative identity is same as additive identity, then it is in fact the 0 ring. Now, I will give you the definition of subring. Like in groups, we have started with a group and then we have defined what is a subgroup. We have seen that it is a subset of a group which is itself a group is called a subgroup. Similarly, here also it is a subset of a ring which is itself a ring is called a subring. So, definition: a subring of a ring R, a subring of a ring R is a subgroup of R, is a subgroup of R, additive subgroup I am saying, is a subgroup of R which is closed under multiplication and contains the multiplicative identity So, which is in other words saying that a subset of R which is itself having a ring structure is in fact a subring. So, examples of subrings, we have seen that Z is sitting inside Q and Z is itself a ring, and Q is sitting inside R which is itself a ring, R is sitting inside C which is itself a ring. So, these are examples of subring. So, Z is a subring of Q, Q is a subring of R, R is a subring of C. So, these are examples of subrings. So, we have seen the examples of subrings. Now, I will go into the next I will define what is an unit element. So, a non-zero element U in a ring R is called an unit if there exists a non-zero element V such that U times V is equal to V times U is equal to identity. That means, in other words, I am saying that unit is nothing but those elements which have multiplicative inverse. So, a non-zero element which has multiplicative inverse is called a unit element. So, let us see example. So, example of units. So, in the ring of integers you can see we have only two elements have multiplicative inverse, one is 1, another one is -1. So, in Z the units are 1 and -1, whereas in Q every non-zero element has multiplicative inverse. So, every non-zero element is a unit. In Q every non-zero element is an unit. Third, as in third example, we can see that in the polynomial ring over real coefficients, which polynomials has multiplicative inverse? Only the non-zero constant polynomials. If we consider any polynomial of positive degree, it does not have any multiplicative inverse. So, in R x every non-zero constant polynomial is an unit. So, we have seen couple of examples of units in a ring. Now, next I would like to define a ring where every element has a multiplicative every element non-zero element has a multiplicative inverse that has a special name which is known as division ring. So, the next definition says that a ring R is called a division ring if every non-zero element is an unit in R. Every non-zero element is an unit in R. So, of course, Q is an example of a division ring, but I will give you some non-trivial example now. So, for example, let us consider H. What is H? H is nothing but A plus B I plus C j plus D k, the elements of this form where A, B, C, D are over real numbers, and I am also having some relations between this I, j and k. What is this? So, I square is same as j square is same as k square equal to minus 1, and I am also having that I j is minus j I is equal to k, then j k minus k j is same as I, and k I equal to minus I k is equal to j. So, these are the relations between this I, j and k. This is satisfied. This is known as the ring of real quaternions. So, this is known as the ring of real quaternions. Ring of real quaternions. So, this is known as ring of real quaternions, and how this is defined. So, we will see that this is this addition and multiplication is defined as follows. So, yeah. So, this addition is defined component wise. So, the addition is defined component wise and multiplication is defined using distributive law. So, let me just give you here with you can check by yourself that this H with respect to this addition and multiplication forms a ring, but this ring is not commutative because you can see that here I j is not same as j I, it is minus of j I. Therefore, this is a non-commutative ring, and let me just clarify about say little bit more about how this addition is defined. So, let us consider two elements. So, say A 1 plus B 1 I plus C 1 j plus D 1 k plus A 2 plus B 2 I plus C 2 j plus D 2 k. So, this addition is defined as A 1 plus B 1 plus A 1 plus A 2, then B 1 plus B 2 I plus C 1 plus C 2 j plus D 1 plus D 2 k. This is how the addition is defined, and I would like to explain the multiplication with the help of an example. So, for example, how this multiplication, so this is how the addition is defined, and multiplication I am saying as follows. So, for example, if I consider 1 plus I plus 2 j, this if I multiply with j plus k, then you can see here using distributive law, this is 1 plus 1 into j plus k plus I into j plus k plus 2j into j plus k. So, then if you simplify this, then you will finally see that this is nothing but coming out to be minus 2 plus 2I plus 2k. And you can see that here every element has multiplicative inverse. So, what is the inverse? So, the inverse of A plus Bi plus Cj plus Dk, the inverse of this is nothing but A minus Bi minus Cj minus Dk divided by A square plus B square plus C square plus D square. So, every element has multiplicative inverse. So, this is a non-commutative ring. So, this is an example of a non-commutative ring, and moreover we know that if in a division ring, if a division ring this multiplication operation is commutative, then it is called a field. So, this is an example of a ring which is a division ring, but which is not a field. So, this is not a field because though every element has multiplicative inverse, but the multiplication is not commutative, that is why it is not a field. So, remark, if a division ring is commutative, then it is called a field. So, for example, Q is a division ring which is commutative. So, Q is an example of a field, but this is a this previous ring, the ring of real quaternions is a non-trivial example, which is an example of a division ring which is not a field because it is multiplication operation is not commutative. Now, let me introduce the notion of a zero divisor in a ring. So, what is a zero divisor? So, let R be a ring, let R be a ring, a non-zero element A of R is called a zero divisor if there exists a non-zero element B in R such that either A dot B is 0 or B dot A is 0. So, here we can see that two non-zero elements are getting multiplied to 0 element. If you see in the ring of integers, it never happens. Two non-zero elements cannot get into multiply and get into a 0 element. But we can find examples of this type, examples of zero divisor in the following ring. So, example, if I consider z quotient 6z, here I can see that 2 bar into 3 bar which is 6 bar, that is nothing but 0. So, here I can see that 2 bar and 3 bar are both non-zero element, but their product is 0 element. So, here 2 bar and 3 bar are 0 divisors. Also, in this ring of 2 cross 2 matrices over real numbers, I can see that I have two matrices, for example 1 0 3 0 and B say consider 0 0 2 5. So, in this case I can see that if I consider A and B to be these two matrices, then A B is nothing but the 0 matrix. So, product of two matrices 0, but none of them is 0. So, these are examples of zero divisors. So, one remark that I would like to make here is the following, that a zero divisor can never be an unit element. So, a zero divisor can never be an unit element. So, let me just outline the proof in 2 lines. So, suppose we start with a zero divisor which is unit, then we should get some contradiction. So, suppose A belongs to R, be a zero divisor which is an unit element. So, since it is an unit element, so that means there exists some non-zero element. So, there exists some non-zero element, say V in R, such that A into V is same as V into A is equal to identity. This is because this is an unit element. And since A is a zero divisor, so since A is a zero divisor, there exists a non-zero element B in R such that A dot B is equal to 0. So, now A dot B is equal to 0. So, if I multiply this on both sides with V, then what do I get? V into A dot B is equal to V dot 0, which is saying same thing as V dot A dot B is 0, and now V dot A is nothing but the identity. So, therefore, this is identity dot B is 0. This implies that B is 0, which is a contradiction. Therefore, we have proved that a zero divisor can never be a unit element. Now, let me just finish with one more definition. So, an element, a non-zero element in R is said to be nilpotent if A to the power n is equal to 0 for some n in the natural number. That means, some power of it is 0, then it is called a nilpotent element. So, for example, if I consider this ring Z quotient 12Z, in this ring we can see that 6 bar is nilpotent, as 6 bar square is equal to 0. So, 6 bar is a nilpotent element. So, you can see here one remark is that every nilpotent element is a zero divisor, but not every zero divisor is nilpotent. And as an example, what we can see? We can see that in Z quotient 12Z, 2 bar is a zero divisor, as 2 bar into 6 bar is equal to 0 bar, but 2 bar is not nilpotent, because no power of 2 bar is equal to 0. So, this is the relation between nilpotent element and zero divisor. So, today I will stop here. These are the references that I have used for this lecture. Thank you.